Hello, I'm Doug Montgomery, and I would like to welcome you to our Fireside chat for the month of February. Uh, I don't know whether you've been around to participate in any of these before, but if you're sort of new to this whole idea, this is something that we do every month, and I always have a guest speaker, and we try to explore specific topics and maybe applications of experimental design concepts. And sometimes we sort of go afield into some other things as well. But we always leave some time at the end of the course for some Q&A. And this is a terrific opportunity for you to ask questions, whether they're about the specific things that we're talking about in our Coursera course, or if you have a general question, or if you have something that's specific to a situation that you're encountering or trying to deal with, we'll try to answer those questions, we try to get to all of them during the Q&A portion of the Fireside chat. But if we don't, then we will try to address them afterwards and get those answers back to you in a reasonable way. We do record these Fireside chats, and they are posted in the resources tab of your course. And you can actually go back and look at other Fireside chats if you want to. There's been quite a number of these, and I've been quite fortunate to have an array of really excellent, outstanding guests, and they've provided a wonderful and rich set of materials that you could really, I think, possibly benefit from. The other thing that I want to mention is that you don't have to wait until the Q&A portion of the Fireside chat begins to generate your questions. You can type them into the chat feature in Zoom anytime you want, and so you can get started doing that anytime you would like. We already have a few that have been submitted, and so we'll probably get to those first. But if you do have questions, you can feel free to type them in at any time. Okay, and with that, I'd like to introduce I should do one other thing. I should remind you to keep your mics off and your cameras off, so that we don't have any crazy background noise interfering with the program or with the recording. Okay, so with that, I would like to introduce our guest, Dr. David Edwards. David is a professor of statistics and chair of the Department of Statistical Sciences and Operations Research at Virginia Commonwealth University. He's another guy that, like me, went over to the dark side and decided to become an administrator. David, I hope you're better at it than I was, because I couldn't stand it. 4 years was enough for me. David earned his BS in mathematics from Virginia Tech. He's another proud Hokie, and an MS in statistics and PhD in statistics from the University of Tennessee. And his research focuses on design of experiments and analysis of experimental data. He has a lot of interest in screening experiments and response surface methods. He's a former associate editor for Technometrics. He's been on the editorial review board of the Journal of Quality Technology and Quality and Reliability Engineering International. He's currently the editor of Quality Engineering. He's has an extensive array of publications. He's a busy guy, and I really appreciate, David, you coming and spending some time with us today. And he's going to talk about a topic that I am intensely interested in. It has to do with non-regular fractional factorial designs. So with that, David, introduction, the floor is yours.
All right. Thank you, Doug. I really appreciate that introduction. And regarding administration, the good news here is at least it's no more than 4 years. And if it's horrible, then there's a way out. That's always positive.
So the sentence has it has an upper bound.
That's right.
It's not necessarily a life sentence. Good.
So I hope you can see my screen without any problem. What I'm going to talk about today is two-level non-regular designs. So I remember my first course in design of experiments, now taken over 20 years ago. And I really, in that first course, found fractional factorial designs to be the most interesting thing. It seemed to have just the structure of those designs fascinated me. I was very interested in how those designs were constructed and even some of the mathematics behind it. And then in the second course in design, we started to learn about non-regular designs. And despite the fact that the aliasing was more complex, they didn't always have this beautiful defining relation. Those types of designs also very much interested me, particularly their flexibility with both run size and the models you could estimate. And so through the years, I've really continued to be interested in the non-regular designs and what structure they might have. Doug, you've done some previous work and with Brad Jones on looking at some defining relations, I believe, with these non-regular designs. And so I'm just really curious in knowing more about what type of structure these designs have, and is there a way to potentially utilize that structure to help us understand the design better, to maybe even augment the design better, analyze the designs better. So that's what I intend to talk about. So I'll give you a bit of detail on kind of what we're looking at here, and then plenty of comments and thoughts on this. So I'm only going to focus on two-level designs, particularly what I would call screening designs, those that are smaller run sizes, but a larger number of factors, where the goal is to identify from the many which of the few factors are truly active. Hopefully along the way, we can also uncover some important interactions as well. So in that first course in design of experiments, you likely encountered what we call the regular 2 to the k minus p designs. And they have these very easy to write out defining relations. And once you're able to do that, then you can understand all of the aliasing structure of that design. And what it does is it separates all of your factorial effects into what I'm going to call alias sets. And you have complete aliasing within the sets, or complete confounding. So for instance, factor A completely equals factor, the interaction AB equals CD, something like that. They are indistinguishable from each other, and they fall into this set that I'm going to call an alias set. Now, the separation into these different alias sets is a good thing. I think fractional factorial designs have seen a great deal of popularity for one reason because of this, because we have orthogonal separation between those sets. You can clearly distinguish whether it's this set that has an impact on the response or this set over here. The nice separation is one of the things that makes the regular designs, I think, so popular, because they're easy to understand and they have a rather easy analysis strategy. But we still have that complete aliasing to deal with. And that complete aliasing means that I can't tell certain factorial effects apart from each other. And maybe that means that I need to do a follow-up experiment or something to resolve that full confounding. Non-regular designs have that much more complex aliasing structure, but it's true that some of these still separate your factorial effects into different aliasing sets that may or may not have some complete aliasing within the sets. So on the downside, non-regular designs may not have as many orthogonal sets of factorial effects, but we can avoid that complete aliasing in a lot of situations. So there's a little bit of good and bad there, but we'll kind of explore these concepts a little bit further. So I'm going to show you two designs here. This is two 16-run, 6-factor designs. They're non-regular, in the sense that they do not have the very simple defining relation that I've been talking about. They cannot be constructed that way. However, if you look at a heat map of the information matrix, so the full factorial model, so in other words, take all the columns of this design and take all possible products and take that matrix transpose times itself and kind of rearrange the columns, you can actually see some structure here. You can see that the design on the left actually has what I would call a block diagonal information matrix, in which I have 4 different alias sets. The one on the right, still block diagonal, and I have 2 alias sets. In both of these situations, you can see that because I have block diagonal information matrix, I have some orthogonal separation. The terms in one block diagonal are orthogonal to the terms in another block diagonal, and so forth. So there is structure with these designs. There is still orthogonal separation. So let me show you both of these designs. 16.6a, again, the design there on the left, actually has these treatment combinations. So I neglected to put column labels on here, or I somehow chopped them off, but think of the labels there as A through F. Okay, so each column they're labeled A, B, C, D, E, F. It turns out if you really look at these designs, you can construct it by concatenating or putting together 4 regular fractions. So in other words, the design in orange at the top, that's just 4 runs, but that would be a 2 to the 6 minus 4 regular fraction. And if you look at it, you can see that, well, factor A, it's all +1s, and factor B is all -1s. And then if you look at what I'm calling C and D, the 3rd and 4th columns, you can see I've got a full 2 squared in those 2 columns. I've got minus, 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 plus, plus, minus, and plus, plus. And then the then column E, that's all -1s. And then the last column is the product of the 3rd and 4th columns. All right, so that is, of course, a regular fraction, very simple defining relation that I could write down for those 4 runs. If you look at what's in yellow, it follows the same pattern. Factor A has all the same signs. They're all -1s in this case. Factor B has all the same signs. C and D, once again, it's a 2 square. E has all the same signs. And then F is also the product of C and D, the opposite of it. And if you look at every set of 4 runs that's present here, you see that same exact pattern. And I've written them over there on the left, but the pattern is exactly the same in those. And when you put them together, all 4 of those fractions together, you get that non-regular design shown on the left here. And we call this fractions from the same family. So all 4 sets there are fractions from the same family of designs, and we call them parallel flats. So nothing really fancy about that name. That's the name that they're given when you have a design that's constructed by combining fractions from the same exact family. We call those parallel flats designs. So it turns out that we could construct the design on the left this way, the design on the right this way. Now this one's a little bit more complicated because now it takes 8 fractions from the same family, all concatenated together. And you might think, well, geez, these are really tiny fractions, and they are. This is 6 factors in 2 runs for every single one of these little fractions. So here we're combining 8 2 to the 6 minus 5 fractions from the same family, just putting them all together. And if you look at the pattern, you'll see A, B, and C are constant in every single one of those sets of 2 runs. And then you're always going to have a plus or minus for D, and then E and F are constructed by some plus or minus of that column D. And so it's also regular fraction. It's just not ones that we typically encounter. One would never run a 2-run 6-factor design in practice. But what we can see here is that we're able to create a design by putting together 8 fractions from the same family. Okay. Now, whether or not you find that fascinating or not, neither here nor there. That's just a matter of the fact that we've been able to uncover that structure for these 2 non-regular designs. Now, what is actually cool about this is that anytime you can do that, anytime you can combine fractions from the same family to form another design, you're guaranteed to have a block diagonal information matrix. That's just guaranteed. Found that out from the literature, and actually it's kind of old literature, 1984 in the Journal of Statistical Planning and Inference. They demonstrated that anytime you can do this, you will always be able to get that block diagonal matrix. Why that's helpful is because you can see all those zeros in there. That means that we've got orthogonal separation of effects. Right? And so the design on the left was 4 fractions together. We call that a 4 parallel flats design. The design on the right was 8 fractions together. We call that an 8 parallel flats design. And the number of distinct flats determines the rank of each alias set. In other words, how many terms could I estimate in each of those alias sets? So again, how is this useful at all? Like, how is knowing that I've got a structure that looks like this block diagonal structure, how does that do anything for me? Because the estimates and parameters belong to different diagonal submatrices, again, they're orthogonal. It means they're uncorrelated from each other. So there's no bias of effects from one group to another group. Right? Large effects in one alias set will not impact parameter estimates from another one. So that's good news. There's still some orthogonal separation. The other thing that's really nice is that you are simplifying the complex aliasing. Right? So non-regular designs have much more complex aliasing. It's harder to understand than the regular designs. But anytime you have that orthogonal separation, you simplify it. The number of linear dependencies is reduced. It's easier to understand. So in a way, you're kind of putting a cap on the complexity by designing your experiment to have this block diagonal structure. So if you have a regular design, and by the way, we call a regular design a single flat design. It's just one flat. All of the estimates are uncorrelated, which is great, but we have that complete aliasing between the effects, which isn't so great. Right? So I'm going to talk a little bit more about bias containment as a benefit of the block diagonal structure closer to the end. But just note that getting rid of that complete aliasing that you have with regular designs, it decreases the amount of separability of the estimates, but we still get some, which is a benefit. So here's just a tiny look at some of the complex aliasing that you might have to encounter with a non-regular design. And what I call a dependent set is a set of effects where if you remove one effect from that set, everything else becomes linearly independent. So if I had a minimal dependent set for the 2-factor interaction model for that first design on the left, some of them were of size 2. So something like A is equal to BE or B is equal to AE. I have some linked 2 dependencies there. I also have some linked 5 dependencies. Those are a little bit harder to understand. Linked 2 is easy to understand. Again, just to kind of relate everything back to the regular designs only have, typically these linked 2 dependencies where you've got this full confounding of effects, whereas things are much more difficult to understand, like the linked 5 ones. It's harder to detangle what's going on there. But as I mentioned, if you can design the experiment to have this parallel flat structure, you are going to cap the length of those dependent sets. So minimal dependent sets can only be of length up to the number of flats plus 1, which means that if I have a 4 parallel flats design, then there can be nothing longer than 5, which caps the complexity. So really the idea is the more flats you have, the more fractions you have to put together to create your design, the fewer alias sets you get, the larger the alias sets get, the more complex the aliasing gets, and the more spread out the correlation gets. So there's this, the way you want to think about it is regular designs, the simplest aliasing has the most alias sets, the smallest alias sets, the simplest aliasing and the most compact correlation, because it's all 100% correlated. As you add more, as you construct the designs with more and more flats, you start to spread stuff out. So what we're looking at here is kind of a compromise. I would like to find designs that are a nice compromise between the regular designs and the most complex non-regular designs, the one that have the most complex aliasing. So how do you determine this? How do you find out if your design is a parallel flats design? Turns out it is super easy to do. It seems like a mysterious concept when you first look at it, but you can take any design and figure out, do I have any parallel flat structure here? And if you do, then you know that you've got a block diagonal structure and separation of effects into alias sets. So that's cool to know. So here's what you do. You just form your full model matrix. So in other words, take your design, take all possible products, two-way interactions, three-way interactions, four-way interactions, all the way up to the K factor interactions, okay? Form that full model matrix. And then look at all the columns. Which ones don't sum to 0? And pull those out, okay? So determine which columns don't sum to 0. Pull those columns out, sort them, and see how many distinct rows that matrix has. That is easy to do. You can do that in pretty much any piece of software, right? Once you've got that design matrix, you can churn this out easy. You can do this in MATLAB, R, Jump, whatever you want. It's easy to extract those columns and sort the rows that are left and see how many are identical. And in this case, this is design 16.6a matrix that you're looking at. You can see there are 4 distinct rows. So there are 4 parallel flats, which means that there's a block diagonal structure. That's cool to know. Just by taking this very simple method here, you can find out I've got a parallel flat structure. So knowing you have it is one thing. Another thing, though, is thinking, well, okay, since I know that there's a benefit to having these designs that are constructed this way, is there an easy way to actually, make the design? And it turns out that there is. And this is just one way that we discovered works pretty well. Isn't the only way. But this method was inspired by a paper from 2020 in the journal Technometrics, written by Brad Jones and his co-authors. And they were talking about what they called group orthogonal supersaturated designs in that paper. And we kind of adapted that to just in general, constructing non-regular designs that have a parallel flat structure. And so whether you care to know anything about Hadamard matrices, a little bit of a rundown here, let HQ denote what I'll call a Sylvester Hadamard matrix. H2 looks like the matrix you see there in the center of the screen. It's got 2 1s in the first row and then a -1 +1. And then you can create an order 4 Hadamard matrix by what we call doubling the order 2. And you can make an order 8 by doubling the order 4 and so forth. So anyways, we're going to let HQ denote a Hadamard matrix. And then T just be any B by C matrix of +1s and -1s. Nothing else I'm going to say about what T should be, just some matrix of +1s and -1s. And if you take the Kronecker product of T and HQ, kind of looks like the matrix you see in the middle of the screen there. The resulting design is going to be a parallel flats design with D flats, where D is the number of flats that T has. Right? So if you just start with some matrix T that has D parallel flats and take the Kronecker product of it with an order Q Hadamard matrix, take the Kronecker product, you've got yourself a parallel flats design. So I'll give you some examples here to make this clearer, I hope. But the reason why this construction is useful is because it guarantees that block diagonal structure for the non-regular design. So I'll start with something that's simple. Let's just let T be a full 2 cubed. All right, 8 runs, 3 factors. You know what that looks like. And then let's let D be columns 2 through 4 of H4. So in other words, You can see right here, that's columns 2, 3, and 4 of H4. Take that Kronecker product, and you get a 32 by 9 regular design. That's, again, not exciting because we know how to construct 32 by 9 regular designs already, but this kind of shows that because T was a full 2 cubed, it was already just a single flat, really. I created another one, just a bigger one. So not exciting, but just kind of helping the proof of concept that, I started with T, that structure of T is important. Example 2 is, instead of starting with the 2 cubed, let's just take the first 7 rows of it. And when you take that Kronecker product now, you get a 28 by 9 non-regular design with 7 flats. How does that happen? Because T has 7 rows, D has 4 rows, so 7 times 4 is 28. And then, of course, I've got 3 columns in T, and I've got 3 columns in D. That product is 9. So I get a 28 by 9 non-regular design. T was a 7 flat design, so T Kronecker D, 7 flat. So now you got a 28 by 9 non-regular design. If you look at the matrix down there, the information matrix, you see it's block diagonal. I have 4 alias sets of size 128 in this case. Well, I've got that orthogonal separation of effects, which means that I'm going to have orthogonal separation of the effects that matter to me. I might have some main effects and 2-factor interactions in one group, and some others in another group, and some others in another alias set, but they're orthogonal to each other, which means that there's no bias if you're in separate groups. If you want to create a supersaturated design this way, you could. And this was the essence of that paper from 2020. They made supersaturated designs, which means more columns than you have rows. And so here's another example of that. Let's let T be the first 10 rows of H16 and D be H4. When you take T Kronecker D, you get a 40 by 64 supersaturated design. And you see that block diagonal structure there when you look at the information matrix. What is interesting here, though, something that we kind of uncovered when we started looking at this, was that in the paper, they said this was a 40-run, 64-column design, which it is. They said it had 4 alias sets, because it looks like it does. When you look at this, you can see here, 1, 2, 3, 4. It looks like 4 alias sets. Turns out, though, that if you rearrange the columns a little bit more, you actually get 8 alias sets. And so there is more orthogonal separation than they led on to in this case. And the reason why is because I need more than just saying that the rank of T is 10 in this case. I need more than just saying, well, I have to know how many parallel flats T has, okay? And this design is not a 10 parallel flats design. It does not look like the structure that they asked for. Turns out that if you just pick T differently, right? You just pick T differently. If you pick T to be a 10 parallel flats design, then when you take that Kronecker product, you get actually 4 alias sets in this case. It's more of a side note than anything. Just kind of looking at, it really does matter how you construct these designs. The one on the left here actually, well, the plot on the left makes it look like there's only 4 alias sets, but there's actually 8. There's more separation than they realized. Okay, so again, that was just a little bit on construction because I think that's interesting. What I really believe is that this provides an opportunity to understand a compromise between simplicity and what we call, maximizing D efficiencies. So the orthogonal design with 32, for example, with 32 runs and 7 factors with the highest D efficiency for estimating the 2-factor interaction model has a D efficiency of 84.32%, which isn't bad. It's a 32 parallel flats design, which means, so check this out, there's 32 runs and 32 parallel flats. If that happens, there is no orthogonal separation, none. So there is no structure really to this design. If I was willing to let the D-efficiency suffer just a little bit, right? Instead of 84.32%, drop it down to 82.56%. I can do it in such a way that I have 16 flats instead of 32 flats, which means that I have some orthogonal separation. In fact, I have two big alias sets, but they are orthogonally separated from each other. So there's still some separation of the effects. That is going to help cap how complex the aliasing is. And so you can kind of see that there's this compromise. The regular design would probably not be able to estimate the two-factor interaction model at all. It would probably have all this complete confounding. So your D-efficiency would be 0 for that regular design. The D-optimal design has 84.32% efficiency, or the D-optimal orthogonal design, but there's no structure really. And here's a design that is kind of a compromise between those two. A little bit simpler aliasing structure, still estimate the model, and I've only lost a little bit in terms of my D-efficiency. So just wanted to point out here is really nothing to go through heavily on this slide, but using that construction algorithm that I was talking about, we were able to come up with some new designs to completely estimate the two-factor interaction model that had these parallel flat structure. So in other words, we didn't have to look at a D-optimal design with absolutely no structure to it. Here are designs that actually do have orthogonal separation of the effects. So, moving forward, one thing I would certainly be interested in doing is checking out these designs a little bit more individually and seeing, okay, do I have an enhanced ability to estimate, not to estimate, but to analyze the data because of this orthogonal separation. So what's the benefit for analysis? I'll mention two possibilities here. One, I believe that's a benefit is what I call bias containment. Okay. Designs that don't have that parallel flat design structure allow for really long dependencies. They're complex, they're hard to understand. There's many terms that are correlated with each other. And what's the downside of that? I mean, the upside, of course, is I can estimate more models. The downside is when you have so many terms correlated that every time you maybe add or drop a term from your model, the estimate's going to change, right? That doesn't happen with regular designs. In fact, maybe you remember the first time you ever explored regular designs, you dropped a term and lo and behold, all the estimates stayed exactly the same because you have really contained the bias into these very distinct alias sets. Parallel flat designs offer a compromise. You're containing the bias still into these alias sets. Not everything is intercorrelated with each other. So I ran a simulation study just to kind of, with the some of the designs on this slide here. And I'm just going to show you a little quick subset of the results. All these designs can estimate the main effects and two-factor interactions, which we say is great. And if there are no higher order effects that are important, then there's no bias that we have to worry about. But let's suppose that maybe there are one or two third order terms that were actually important. We don't often detect those. We don't often look for those types of terms. But let's suppose that maybe one or two of them were actually active. And I estimated the two-factor interaction model. And let's suppose that, let's start all the way to the left, okay, with main effect estimation. And let's suppose that no third order terms were active. You can see that the bias is pretty much the same for the parallel flats design and the D-optimal design. They're about the same, okay? If there really is no large active third order terms, it doesn't matter. But if you look at the middle one that says there's one active and the one to the right says there's two active, you can actually start to see this uptick in bias when you move to a D-optimal design versus the 8 parallel flats design. Okay. And that's because everything's so intercorrelated with each other with the d-optimal design that, you end up with this larger bias. Whereas you have more bias containment with the parallel flats design. And if some of the terms in an alias set in the parallel flats design is correlated with the third order term, that would increase. You'd have a problem there, but it wouldn't affect everything else. And if you look at the two-factor interactions, you see exactly the same thing. You're seeing, well, if there aren't any active third order terms, everything looks good, no problem. As you start to have some active third order terms, you have some problems with using the d-optimal design versus the parallel flats design in terms of third order bias. Now, I think that something like this also works nicely for group orthogonal supersaturated designs, because here you could explore two-factor interaction bias. And that is really, I think, one benefit of these Go SSDs that Brad Jones and others came up with. They're really clever. You can imagine what you can do with these designs. You've got these groups of factors, orthogonal groups of factors. And with the initial analysis, maybe you uncover what you call an active alias set. You say, all right, there is something in this set of factors that's really important. And you zone in on that alias set and you decide, oh, a few of these factors are definitely important. And then, with any good design strategies, especially if you're doing supersaturated screening, you probably should follow up with an additional experiment to confirm your results. And let's say you do that, and then you refute that factor activity. You're like, oh, wait, that factor isn't showing up as important at all. Turns out maybe it was due to some large two-factor interactions. But because you know that those factors are correlated with certain two-factor interactions in that alias set, it might help you readily identify which interactions may have caused that factor to appear active. And so it really helps you, I think, better handle the analysis. Here's a possible design-based analysis strategy. This is something that we're working on and something that I'm definitely very much so interested in exploring. But one possible strategy would be to perform some sort of variable model selection strategy separately for each alias set because they are orthogonal to each other. So instead of the observed response, you would use this kind of altered response that's obtained by using what we call the projection matrix. And so if you take and multiply the projection matrix involving the terms in the jth alias set times the response, you get this, what I'm calling an altered response, and use that to analyze each alias set. So you perform the same analysis strategy on each alias set, and then you ultimately combine your results to say, this is the model that I'd recommend. I think this is very much so skeleton strategy at this point. A lot of things to investigate here, and I'm always open to additional suggestions. So some final thoughts. Searching for designs with linear dependencies as large as possible tends to produce designs that have no block diagonal structure. And what happens is you end up with correlations all over the place. And yes, that does help with estimating more models, right? So if you're trying to do something like make your estimation capacity as large as possible, make your d-efficiency as large as possible, maybe that's the way to go, but you lose structure. You make the aliasing much more complex. The benefit of having this these parallel flat designs is that you get that orthogonal separation of effects that has simpler aliasing that's more readily understood. So this is something that's kind of in motion. We just had a paper appear on this. It's in press actually in JASA that kind of goes through all of these details. If you're interested in learning more, but there's, I think, much more that we can do, particularly on the analysis side. What can we do to really come up with really great design-based analysis strategies that really take full advantage of this structure? And with that, that's all I've got as far as what I wanted to share with you. I'll stop sharing my screen now.
David, thank you. This is an extremely interesting talk. I enjoyed this a lot. I've had an interest in non-regular designs myself for a number of years. And I'll tell you a little bit about sort of my motivation for doing this. For the last 7 or 8 years, I've been part of a research consortium that's funded by the Defense Department. And what we're doing is we're trying to look at developing test and analysis methodologies to improve the way that the DoD does what they call operational testing. Operational testing is something that they're required to do. Congress passed some laws about this back in the 60s. But basically, you have to take every new system and you have to test it in the field under normal, operating conditions and find out how it works. And this leads to some experiments that have fairly large numbers of factors, 6, 8, 10 factors. And your time that you have available, the funds that you have available, the equipment and other resources that you have available to do these tests are kind of limited. And so that leads to the idea of fractional factorial designs. And so now you'd like to be able to estimate the effects of these factors. And there are probably going to be interactions. And so, we've explored the use of non-regular fractional factorial designs for doing this. And it turns out the idea seems to work pretty well. And we've also looked at the different analysis methods for the types of non-regular designs that we've been looking at. And so I have a lot of interest in this topic, and I really, really enjoyed your talk. And I think, as you point out, there's lots of opportunity in terms of creating not only new designs in this area, but analysis methods as well. So congratulations on doing some really nice work. We have questions.
I am hoping.
Yep, we have questions, and there's one that's up on the screen. Let me go ahead and read this. Can you see the question, David?
I can't, unless it's on the, is it in the chat?
No, it's on the screen that's projected in front of me, but don't worry, I'll read it. Okay. So it says, this question is for both of us, because I'm a PhD student and I study plants and its interaction to light, carbon, and temperature. And so using fractional factorials can save me a lot of resources and time. He says, but I'm having a difficult time convincing my supervisor about the usefulness and practicality of fractional factorial designs. He's worried that I may have to explain the whole concept in my publication for biologists, who will be the reviewers, who don't have sufficient interest or understanding of DOE. And there's concern about that interpretation of the results is not as simple to communicate because the underlying mathematics is not familiar to the biologists who lack the training in DOE. And so he wanted to hear our thoughts on this, and what do we think about this? David, you probably have in your situation at the VCU, you've probably dealt with exactly this kind of problem on the academic side. I have a little bit of background here, but maybe not as much as you.
I have found that, and I don't know if I think it's discipline specific. I have found that engineers are very comfortable with full factorials. And as soon as you start talking about fractional factorials, that kind of piques their interest as well. They're willing to explore that. And you're right, I haven't seen as much as far as on the biological life science side, but I certainly have encountered their use. And I wonder if I'm not sure. I'm honestly not sure why it might be difficult to convince them about the practicality of them. What I would typically do is search for articles that in perhaps in your field that have used these, and look for how was it presented in those articles? How do they analyze the results in those articles? Because if that's the case, it tends to be easier, I think, to convince someone, oh, well, it's been done in this field before, not without a problem.
Yeah, and I think being able to cite some of that work in your own publication when you submit it is helpful. And even if it's not an exact fit, you can find something in an allied field that carries or conveys the same message. I've had a little bit of experience working with some of our life science folks, because we have a faculty member who has a joint appointment there, and I've worked with him some, and there's a project ongoing with having something to do with insect colonies, and I won't go into all the details of it, but that group has become pretty receptive to some of these kinds of techniques, because they've seen that you get results. And so I think you just have to be kind of diligent to search out some literature that it might not be exactly what you're doing, but as long as it's an allied field, I think people will figure it out. A lot of this work in experimental design began in agriculture and life sciences. So they're not probably totally unfamiliar with what's going on. Yeah, I think he's being a little bit pessimistic. Okay. If we want to increase the power of a randomized complete block design, is it better to increase the number of blocks or the number of replicates within blocks? And the textbook implies it's better to increase the number of blocks. And is it better to say have 4 blocks times 2 treatments times 1 replicate, or have 2 blocks times 2 treatments times 2 replicates? Can you explain which one is better and why? Well, let me sort of address this from a general viewpoint, and then see what you have to say, David. But in most of the experiments that I've encountered involving blocking, it's easier to run more blocks than it is to increase the number of runs within a block, because very often the block size is very fixed. You can't change the block size very easily. If days are your blocks, you can only do 4 runs a day. Okay, you can't squeeze 8 runs into a day, or if batches of material are your blocks, you can only produce so many runs out of a batch of material, and so trying to do more runs within a block is often much more difficult from a practical viewpoint than increasing the number of blocks. At least that's sort of been my experience, and that's probably why I sort of lean in that direction in the textbook. But your thoughts on this are very welcome, David.
I don't disagree with what you said at all. That was pretty much going to be my answer as well. You can think of, every time you run a treatment combination in a block, it's a complete block, so you are still replicating. So you're still getting that replicating benefit. But I completely agree with having more blocks.
Yeah, and as I say, from a practical viewpoint, that is usually so much easier, just because of the physical limitation of the size of the block. Good question. Okay. I have designed a 2 to the 4 design, 1 very hard, 1 hard, and 2 easy to control, or I guess easy to change factors using jump, and set the criteria to D optimal. But under design diagnostics, the D efficiency, nor I or G efficiencies, but he was given an average variance of prediction of 1.770999. And he says, I wonder if I made a mistake in creating the design. Well, I wouldn't think so. The dialog box here for creating this design is pretty straightforward. you're able to identify the factors as very hard to change, or easy to change. And you have some control over the number of runs that you make. And maybe the result of this average prediction variance being 1.77 is a function of the number of runs that you chose to make. If you use something other than the recommended number of runs, that average prediction variance could change. David, what are your thoughts on this?
So I was trying to make sure I understood the question. If it was saying that the average variance prediction was given, but they didn't get any D, I, or G efficiency. So it was, I guess they were all blanked out and then the average variance prediction showed up. I'm wondering if that was what the question was.
Yeah.
And I normally only see that when the model that is asked for is more in the Bayesian optimal sense, where the design can't estimate that complete model. But I probably need more details to know for sure why that happened in the split plot case here.
Well, even with the split plot structure, you should be able to estimate all the main effects and interaction effects. It's a full 2 to the 4.
Yeah.
So something's this I'm not, and of course I've seen designs that have different D efficiencies and of course different average variance of prediction, and it is sometimes a function of how many runs you choose to make. The impression I get here is he's doing all 16 runs of a full 2 to the 4.
Yeah, it's what it sounds like. I would, unless there's just some sort of perhaps JMP doesn't provide those values for the split plot designs. I'm not really sure. I
yeah, that's a thought. I don't know that, but I'm sort of under the impression that it does. But I don't know. It may be that you don't get that with the split plot. I wonder, they're probably doing this on the custom design feature in JMP. I may afterwards try to take a look at this and see if I can get some idea of what's going on here. Interesting question.
Yep.
By the way, that might also be something that you can inquire with the JMP folks about. The JMP help is really good, and you can call the JMP hotline number. Okay, and, it's like Crime Stoppers for experimental design. You can call that, and they're very helpful. And if the folks on the line don't know the answer, they'll get it figured out and get back to you. So that would be another avenue I'd suggest you take a look at. Okay. Oh, this is a long question. I have a question regarding covariance and the analysis of covariance. This is in chapter 15 of my textbook. Some situations I encounter in my engineering job were very much like your example in table 1510, breaking strength and diameter of fibers as the covariate variable. A measurable covariate variable is expected to affect the response in an experiment. Up to now, I've dealt with these situations differently and would like to know whether my intuitional approach has drawbacks or is altogether erroneous. He says, here's what I do. I usually try to transform the response with respect to the covariate. In the case of the example from table 1510, the easiest transformation would be the new response, y prime equal y over x. But I would probably have chosen y prime equal y over is x squared. This is more logical from the physics of the process. So my response would not be the breaking strength, but the breaking strength per cross-sectional area, and then do the analysis in the same, as usual. And he says, in my approach, I don't need the assumptions of beta different from 0, although the division of x as a random variable would probably inflate the error of y prime as compared to y. But checking regression on y of x versus y before transformation should take care of that. I don't need to assume no interaction of beta and treatment, as any interaction would simply show up as the treatment effect. I don't need to neglect higher order terms. And the advantage of my approach is the simple analysis and the fact that I'm not restricted to linear transformations. But I suspect there may be disadvantages too, and what are they and what am I missing? Well, there's certainly nothing, at least David, interested in your comments too, but there's certainly nothing unreasonable about the kind of transformation that you suggest. And if the response of strength per cross-sectional area makes engineering sense, then there's no reason not to do that. I've done that sort of thing myself, but there are many times where you have situations where that kind of relationship is not very obvious. Particularly in chemical processes. If you have a variable that you're interested in, and some sort of performance characteristic of the material, of the chemical, and the covariate is something like viscosity or molecular weight, there may not be some simple mathematical connection that works very well that produces a result that's intuitive and useful. So I don't see, while I don't see anything wrong with what he's proposing, I can see situations where it would not be as intuitive to implement. And by the way, you can have more complex covariate models. They don't have to be linear, and you can have multiple covariates. That's the advantage of the covariance approach. For example, your covariance might be viscosity and molecular weight. So now you're kind of stuck. You've got two of these covariates. So while I think his approach is not unreasonable in simple situations where the transformed variable has a meaningful engineering or practical interpretation, it's probably not general enough to say that it's a complete substitute for doing covariance analysis.
Yeah, the analysis kind of reminds me of dimensional analysis when what he's doing. I know it's not exactly
Right.
the same thing, but incorporating that information into the response is completely legitimate, and
Sure.
it simplifies your analysis, and there is no harm with that. I mean, if you're really curious, what you might do is run your analysis both ways. Run it with treating it as a covariate in the model and with the transform data, and see, are you getting pretty much the same results? Are you explaining more variation with the analysis of covariance model instead?
Right.
If you're really curious as to what the differences might be, but I don't see any disadvantage to your approach because it uses your engineering or physics knowledge.
Exactly. And that may improve the interpretability of the results to the end user. So nothing wrong with that. We're getting toward the end. Our technical folks are telling me to shut up. We're getting toward the end. David, I want to thank you very much for taking time out of your busy schedule. As a department head, I know exactly how busy it is. You probably already have a line of 20 disgruntled people standing outside your office to complain about something. One of the most useful decorations I had in my office at Washington is I had a framed sign on the wall that said "No whining," and
I'm gonna have to get that.
Yeah, you might find that useful in your job. But at any rate, this ends the question and answer session for today. Our next Fireside Chat is scheduled for Wednesday, March the 9th. And information on the topic, the guest, and how to join is going to be included in the Design of Experiments Coursera course. Thank you all for coming. And once again, thanks to David Edwards for such an interesting, to me, fascinating presentation. And these non-regular designs continue to be really exciting things. Thanks again.
Thanks, Doug.